Our universe is a vast and mysterious place. It's filled with billions of galaxies, each containing billions of stars. But what we see, all the stars and galaxies, makes up only a tiny fraction of the universe. The vast majority of the universe is made up of something we can't see, something mysterious and invisible. We call it dark matter and dark energy. Dark matter and dark energy don't emit light or energy that we can detect with our telescopes. We know they exist because of their gravitational effects on the things we can see, like stars and galaxies. Dark matter acts like an invisible glue, holding galaxies together. Dark energy, on the other hand, is a mysterious force that's pushing everything in the universe apart at an accelerating rate. By understanding these mysterious forces, we can unlock the secrets of the universe's past, present, and future. To understand dark matter, we need to go back to the very beginning, to the Big Bang, the event that created our universe. In the first moments after the Big Bang, the universe was an incredibly hot and dense soup of elementary particles. As the universe expanded and cooled, these particles began to combine, forming protons and neutrons, the building blocks of atoms. However, there was another type of particle present in those early moments, one that didn't interact with light or other particles in the same way. These particles, known as dark matter particles, didn't clump together to form atoms. Instead, they remained scattered throughout the early universe, interacting primarily through gravity. The exact nature of dark matter particles is still a mystery, but scientists believe they are likely to be weakly interacting massive particles, or WIMPs. These elusive particles from the early universe play a crucial role in the universe we see today. In the early universe, gravity caused small fluctuations in the density of matter to grow over time. These denser regions attracted more and more matter, eventually collapsing to form the first stars and galaxies. However, ordinary matter alone couldn't have created the large-scale structures we see today. Because dark matter doesn't interact with light, it wasn't slowed down by the radiation that filled the early universe. This allowed dark matter to clump together faster than ordinary matter, forming a cosmic web of filaments and halos. These dark matter halos acted as gravitational wells, pulling in ordinary matter and providing the seeds for galaxy formation. The gravity of dark matter helped to shape and structure the galaxies we see today, creating the spiral arms of galaxies like our own Milky Way. Dark matter acts like an invisible scaffolding, providing the gravitational glue that holds galaxies and galaxy clusters together. For centuries, astronomers believed that gravity was the only force governing the universe's expansion. They assumed that the expansion, triggered by the Big Bang, would gradually slow down over time as gravity pulled everything back together. However, in the late 1990s, two teams of astronomers made a startling discovery that turned our understanding of the universe upside down. They were studying distant supernovae, exploding stars that emit incredibly bright light, to measure the rate of the universe's expansion. To their astonishment, they found that the expansion of the universe wasn't slowing down, it was speeding up. This force, which we now call dark energy, makes up roughly 68% of the total energy density of the universe. Imagine throwing a ball into the air. You expect it to go up, slow down, and eventually fall back down due to gravity. Now imagine throwing the same ball, and instead of slowing down, it keeps going faster and faster. That's what dark energy is doing to the universe. It's like a cosmic anti-gravity pushing everything apart at an ever-increasing rate. One leading theory is that dark energy is a property of space itself. Even empty space, the vacuum of the universe, could possess a subtle energy that exerts a repulsive force, pushing space itself apart. The cosmological constant could explain why the universe's expansion is accelerating, but it also raises new questions about the nature of space and time. The discovery of the accelerating expansion of the universe was a watershed moment in cosmology. It provided the first concrete evidence for the existence of dark energy and revolutionized our understanding of the universe's fate. But how do we know for sure that the universe's expansion is accelerating? One of the key pieces of evidence comes from the observation of distant supernovae. These exploding stars serve as standard candles because their intrinsic brightness is known. By measuring how faint these supernovae appear, astronomers can determine their distance from Earth. Observations have shown that distant supernovae are fainter than they should be if the universe's expansion were slowing down. This dimming suggests that the supernovae are farther away than expected, meaning the universe has expanded more than we thought it would have in the time since the light from those supernovae was emitted. If dark energy continues to dominate the universe's expansion, as current observations suggest, the universe will continue to expand forever, and the galaxies within it will become increasingly isolated from one another. The discovery of dark energy has presented physicists with one of the most profound mysteries in all of science. What is the origin of this mysterious force that's driving the universe apart? One possibility is that dark energy is a cosmological constant, an inherent property of space itself. As space expands, so too does the amount of dark energy, leading to an ever-increasing acceleration. This idea, while simple, raises questions about why the cosmological constant has the specific value it does. Another theory suggests that dark energy is not a constant but a dynamic field that changes over time. This field, known as quintessence, could arise from new particles or forces that we don't yet understand. Quintessence models offer a more flexible explanation for dark energy, but they also introduce more unknown parameters. A more radical idea is that our understanding of gravity is incomplete. Perhaps on cosmological scales, gravity behaves differently than we expect, leading to the observed acceleration. Despite their elusive nature, scientists are actively developing new ways to study dark matter and dark energy. These investigations involve a combination of astronomical observations, particle physics experiments, and theoretical modeling. Each approach aims to shed light on these mysterious components of the universe. Astronomers are searching for the telltale signs of dark matter's gravitational influence on visible matter. By studying the rotation of galaxies, the motion of galaxies within clusters, and the bending of light around massive objects, they can map the distribution of dark matter throughout the universe. Particle physicists are searching for the elusive dark matter particles directly. Experiments deep underground, shielded from cosmic rays, are looking for the faint signals that might indicate a dark matter particle colliding with an atom of ordinary matter. Theoretical physicists are developing new models and simulations to understand the properties and behavior of dark matter and dark energy. These models help to interpret observational data and guide the search for new particles and forces. In the early universe, dark matter and dark energy shaped the cosmos. Their interplay determined the rate of expansion and the formation of large-scale structures. Dark matter's gravity pulled matter together to form the seeds of galaxies. This pull counteracted the expansion driven by the Big Bang. As the universe expanded, dark energy's influence began to take over. This marked a turning point in cosmic history. Roughly 5 billion years ago, the universe's expansion began to accelerate. The balance between dark matter and dark energy was crucial for the structures we see today. The discovery of dark energy has profound implications for the ultimate fate of the universe. As dark energy continues to drive the universe's accelerating expansion, the galaxies we see today will become increasingly distant and isolated from one another. Over vast cosmic timescales, the expansion driven by dark energy will have several consequences. First, it will stretch the fabric of space-time, making it more difficult for light from distant galaxies to reach us. As a result, future astronomers might only be able to observe a small, local region of the universe. Second, the accelerating expansion will influence the evolution of galaxy clusters. While gravity currently holds these massive structures together, the increasing dominance of dark energy will eventually overcome gravity's pull. As a result, galaxy clusters will disperse, and new galaxy formation within clusters will cease. Finally, the accelerating expansion will affect the universe's overall energy density. The study of dark matter and dark energy represents one of the most exciting frontiers in modern science. While we have learned a great deal, many questions remain unanswered. Future research will focus on unraveling the true nature of dark matter and dark energy. One pressing question is the identity of dark matter particles. What are these elusive particles? Another challenge is understanding dark energy. The study of dark matter and dark energy is a global endeavor.